this video, we'll focus on a very important technique for understanding limits of sequences. That is applying L'Hopital's rule. So let's start with an example. an equals natural log of n over n. As n goes to infinity, the numerator is going to infinity, and the denominator is also going to infinity. So how do you understand these limits of the form infinity over infinity with L'Hopital's rule? What does that tell us is that the limit as n goes to infinity of an, which is the limit as n goes to infinity of natural log of n over n, is equal to the same as the limit as n goes to infinity of the derivative of the numerator over the derivative of the denominator. So I'm using this prime as shorthand for taking the derivative with respect to n. Okay, there's a problem here, which is you can take the derivative of a function of real numbers. But here, an isn't really a function of real numbers, right? Like we know what a1 is, a2, a3, a4. But what is a pi or a square root of 17? It turns out we don't need to worry about this. So the idea is if we can find a function, let's call it f of x, where when you put in a whole number n, you get an, and the limit as x goes to infinity of f of x exists, then so does the limit as n goes to infinity of f of n. And the whole point here is that this is the limit as n goes to infinity of an. So this expression I wrote down here doesn't totally make sense, because when n is just a positive integer, how do you take a derivative? But now the idea in this example is we just let f of x be equal to natural log of x over x. And we know from this fact that the limit as n goes to infinity of an is the same as the limit as x goes to infinity of f of x. And here we're going to apply L'Hopital's rule and say that this is the same as the limit as x goes to infinity of the derivative of natural log of x with respect to x over the derivative of x with respect to x. Okay, and what is that? That's the limit as x goes to infinity of 1 over x, the derivative of natural log of x, divided by 1, the derivative of x. So this is just the limit as x goes to infinity of 1 over x, which is 0. So this sequence converges. So you might be nervous about applying L'Hopital at first because sequences are defined for the positive integers. But it's okay. If you can find a function of a real number that agrees with your sequence for positive integer values n, then you can just find the limit of that function instead, so we can apply L'Hopital. So I'll pause, and I'll do one more L'Hopital example. Let's look at this sequence. an equals 1 plus 1 over n to the nth power. So as n goes to infinity, what's happening? 1 plus 1 over n is going to 1, but we're taking something to a higher and higher power. So we're getting a limit that looks like maybe like 1 to the infinity. But it's not quite equal to 1. It's something a little bit bigger than 1 that's approaching 1. So here we have to do something like a little more sophisticated. The first thing we want to do is this idea that we talked about at the beginning of the video, is we're going to consider, instead of n, let's look at the limit as x goes to infinity of 1 plus 1 over x to the x. If the first limit exists, the second limit also exists, and they're the same. So what we're going to do is we're going to show that what the second limit is, this limit here, and then conclude that it's equal to the limit of the first sequence. But how do you understand a limit like this? So this is an idea that is a little bit trickier than the stuff we've done so far with limits, but it's important, so you should get comfortable with it. The idea is that the x in the exponent is something we would like to get rid of. This is a little tricky. So what we're going to do instead is take logs, take natural log. So that's the key idea. We're going to let y be equal to 1 plus 1 over x to the x. And instead of trying to understand what y is, we're going to look at natural log of y, which is x times natural log of 1 plus 1 over x. Because when you take the natural log of something raised to a power, that power comes down and multiplies your log. Okay, so now what's going on is as x goes to infinity, the first term is going to infinity, and log of 1 plus 1 over x, well, x is getting large, so this is going to 1, and log of 1 is equal to 0, so this is going to 0. So we're getting something that looks like infinity times something that looks like 0. So again, not so easy. But there's an idea that works really well where you can turn a limit that looks like infinity times 0, often with a little bit of manipulation, into one where you can apply L'Hopital's rule nicely. So the limit as x goes to infinity of x times natural log of 1 plus 1 over x is the same as the limit as x goes to infinity of natural log of 1 plus 1 over x divided by 1 over x. Why is this better? Because as x goes to infinity, now the numerator is going to 0, and the denominator is also going to 0. So this is a 0 over 0 type limit. And the idea is to apply L'Hopital's rule. So what does that say? This limit is equal to the limit as x goes to infinity of the derivative of the top with respect to x divided by the derivative of the bottom with respect to x. And we know what these derivatives are. So the limit as x goes to infinity, natural log of 1 plus 1 over x, we get 1 over 1 plus 1 over x. But then we have to apply the chain rule. We need a derivative of the inside. This is x to the minus 1. So we get is minus 1 times x to the minus 2. We get a minus 1 over x squared. And in the denominator, we just have the derivative of x to the minus 1, which is minus 1 over x squared. So these terms cancel. And what we get in this limit is the limit as x goes to infinity of 1 over 1 plus 1 over x. As x gets large, we're getting something that looks like 1 over 1 plus 0, which is just 1. So now we have to be a little careful. This is not the limit that we started with. This is not the limit as n goes to infinity of an. We replaced n with x, and we set y equal to 1 plus 1 over x to the x. So we want to know what happens to y as x goes to infinity. But the limit that we just did isn't y, it's log y. So we see that log of y goes to 1 as x goes to infinity. So if the natural log of something goes to 1, then what is that something going to? So that means that the limit as x goes to infinity of 1 plus 1 over x to the x has to be equal to a thing where you take natural log and you get 1. So it has to be e. So what does that mean? If this limit of y is equal to e, this limit exists, and it's equal to the same as the limit of an. So this means that this an right here, this converges, and it converges to e. So one kind of fun thing to do is plug this into a calculator, like for a couple of values of n, like n equals 1, n equals 2, n equals 3, n equals 10, n equals 50. And what you'll see is that you're getting something that gets closer and closer and closer to the decimal expansion of e that you've seen before.